so fun to be here and to be introduced to speak to all of you, and especially by one of your best friends. It meant a lot. And I hope I can live up to all aspects of that in this talk today. I'm just thrilled to be here. Thank you so much to the organizing committee and the steering committee and the incredibly hard work that you all have done to make this such an incredible meeting all the way through. I've just loved it. It is one of my favorite societies, and these meetings are always so rewarding in so many different ways. What a thrill. It's just been great. Well, when I got the topic for the meeting and I began thinking about my plenary talk, I thought, well, this is going to be easy. The topic is so nice and narrow. Water connects. Okay, well, it is a great theme because we can all relate that phrase to our careers. We can relate it to each other and the ways that we collaborate and have fun and do the science that we do, and the way that it engineers quietly our whole entire lives and the interactions that we have. So I do love the theme, and I will be relating some stories to that theme throughout my talk. I'm looking at the opening slide there, and I just also have to add to the accolades for the organizing team that this logo really tops all of the incredible ASLO logos over the years. I love it. Did you guys, I don't know if you were all at the opening plenary where some of this was described, but you know, that's a drop spindle, the top of a drop spindle, which is used for spinning and for spinning wool. And you can see there all the beautiful different kinds of aspects of water that are all connected. And then when that little wheel is spinning, they all kind of merge together. And as a daughter of a spinner, my mom spins and weaves and all that. And I remember using a drop spindle when I was little, and it is very mesmerizing, and it can in fact make you fall asleep. So try not to stare at it too much at the end of the long meeting. Thank you all so much for sticking it out. Our program also talks about water as the gossamer of life, and you know, indeed it has us in its fold, like the spider web all covered in dewdrops. Water connects us from molecular levels to global and galactic ones, right? Water regulates the way this universe works, and it has so many interesting properties, including surface tension, which is helping these little droplets hold together. And as we teach our limnology classes, we often use this picture, right, of the little water strider scooting around on surface tension to portray the strength of those hydrogen bonds. And I think it's easy to take that for granted, right? I mean, we forget how incredibly weird these properties of water in fact are. This is a strange thing. And I think that we can think about this strange, like, surface tensions of water from this sort of molecular scale all the way up to a planetary one, where surface tensions come to mean something else, where we have a world that has incredible pressures on its water resources as our populations grow, as we more wastefully use it, and our supplies of clean water are dwindling with climate change. And so I do want to spend a little bit of time talking about that kind of like global scale surface tension. And this is a map that was generated to show the areas of the world that are most at risk for dangerous kind of conflict around water based on their history of disputes over water. And it's not surprising, you've probably all seen this, that these areas in Asia and in East Africa and all over the central Middle East are really hot spots for water conflict. because there have not historically been institutions there to really mitigate, directed at mitigating water conflicts at different scales. And these authors go on to talk about other regions where conflict mediation is coming into play because of really novel community bottom-up based mechanisms of promoting adaptive and resilient solutions. But sometimes when I look at a map like this, I think, wow, it's so extreme, and it's hard to imagine solutions, and it's easy to get frustrated. But then I look out at all of you, and I'm not being trying to be corny here. It's incredible the work that's being done in this room, and we can turn to the person sitting next to us to say, wow, there's some inspiration there. We're using an incredible base of knowledge to begin solving some of these really huge global struggles over water. And we can probably turn to folks within our institutions as well, and I'm thrilled to be able to do that at FIU. Here I'm just showing Elizabeth Anderson. She runs our Tropical Rivers Lab, and she's working all over the tropics with all kinds of communities that are stressed over dwindling water supplies. And this picture shows her seated with her team over in the Mara River Basin. This is a river that drains into Lake Victoria that has historically been very stressed in terms of its water supply, and very stressed now as a result of increased droughts and drying due to climate change. And just in a very short time, in a few short years of being funded by a wonderful philanthropic organization, the MacArthur Foundation has come in to help Elizabeth and this team, and they've come up with some incredible tools. She has local folks developing sensors, deploying sensors in rivers, collecting water quality data, talking about the ways in which you go about biological resource assessment, putting into place these kinds of scenarios workshops where everybody can get together and talk about what could the future look like, what do we want to see, and how can we get there? And they're starting to implement those approaches, and it's really, really inspiring. And I think we find this inspiration all around our field, and it's just really motivating to see. So here's an example from one of the most stressed regions of the world with the least means of inherently solving these problems. And now I want to turn to a region that doesn't have any excuse. It's a most water replete place on the planet. One of the most water replete places with a long history of thinking about water and resources available for dealing with water, yet we maintain a situation where we're grappling with the future of water, and that's South Florida. The left-hand panel there is a really cool image. It's a recreated satellite image of what South Florida probably looked like 100 years ago. And you can see there are these incredible plains of sawgrass meadows and prairies that graded eventually into coastal mangrove forests and out into the Gulf of Mexico as one continuous incredible subtropical paradise that over time became a real draw for people to colonize and to begin really deconstructing. And we've taken over the last century a lot of that precious fresh water, and we've channelized it into thousands of kilometers of canals that then dump it directly into the sea. Goodbye. And that picture on the right then shows a modern satellite image showing all the compartmentalization that's gone on, the canals there in the upper right around the agricultural areas. They're not only dumping the water out to the sea, but the water is now all full of pollutants, and those pollutants have been long known to cause all kinds of troubles to this hyperoligotrophic Everglades. and then the growing population of Miami continuing to put pressures on that dwindling water supply. So here we are in a water replete region with all kinds of water availability problems. And our ecosystem of the Everglades, which hydrates this aquifer below it that's on limestone and that supports like 9 million people, 1 out of every 3 people in Florida. That ecosystem is not just sitting by and by on the porch waiting for the cows to come home. It's not. Ecosystems don't do that. They don't sit around and wait. It is changing in all kinds of ways that bring into question the possibilities for its future. And we do have an incredible plan for its future, and it's called the Comprehensive Everglades Restoration Plan. This was a plan that was just finishing being constructed during the time that I first started about 20 years ago down in Florida. And it's signed into law by the federal government and the state government of Florida that have said, yes, this is what we're gonna do at the cost of $8 billion then. We're gonna take that water that is all diverted and being dumped to the sea and put it back into the Everglades and restore the biodiversity and incredibly weird functionality of this ecosystem and all the incredible services that it provides, including that fresh water. And over the last 20 years, we have seen some cool things happen. We had the river draining into Lake Okeechobee had been channelized, and one of the first pieces of the Everglades Restoration Plan was to put the kinks back in. That's a huge engineering upon engineering endeavor, and they did that, and it's really successful and very interesting and cool. And yet, until the last couple of years, we wait and we question when. And as we think about the changes that are happening inherently in this ecosystem that is a freshwater ecosystem that's dependent on this gossamer of life, fresh water, it sits and dries and changes as a result. And so we may ask whether restoration is possible, and indeed are talking quite a bit more now about rehabilitation. All of that is happening as we have a rate of change in our climate pressures that is unprecedented and is accelerating beyond what we could have predicted back then. And here we show the sea level rise rate developed by the predictions developed by the USGS in support of our Southeast Florida Climate Compact. This is a really progressive organization putting together some really neat plans for building resilience in this community of South Florida. And in looking at this, okay, you've got sea level rise in inches on the left, and well, just in case, you've got feet on the right. And I am sorry that I'm gonna toggle between English and metric units throughout this talk, because I've got some public and scientific stuff in there. Anyway, we're gonna have a couple of feet of sea level increase happening over the next couple of decades. This is crazy. And this is happening in an ecosystem that is really, really flat and really underlain by porous limestone that's like Swiss cheese and doesn't do anything to prevent this water from coming in overland and underground. And there you can see the areas that are less than 10 meters and areas that are less than 5 in the darker blue. And the Rock Reef Pass in the Everglades, the highest point of 3 feet. This is danger for the Everglades. And even more so in the recent years, our LTR folks, Shimelis Desu recently published a paper on what's going on with the water balance in the sloughs of the Everglades, and used the tidal gauge at Key West to look at sea level rise. And one of our other collaborators, Shimon Wedowinski, has been analyzing these changes. And this is a heat map. It's showing changes on a monthly scale on the X and over the years, a 100-year record on the Y. And you can see there that the rate is increasing, and it isn't increasing linearly, and it is going beyond what that global rate of rise is of 3.5 millimeters a year. We're between 10 and 20 in the last decade. And this seems to have something to do with the slowing down of the Gulf Stream, and it's confusing, and we're trying to figure it out, but it is something that is influencing our day-to-day lives in Miami. And you've probably seen this in the news where the water is coming up on the streets of Miami during our king tide events. That's the original tides that happen a couple of times of the year. And when you want to get something to happen in terms of action, you flood the dance clubs of South Beach, right? I can't dance in water like this. Something must be done, and so what do? They take the water, they build a bunch of big pumps that we're really good at doing in Florida, and we shunt it out to the sea, in fact, into Biscayne Bay, one of the most pristine estuaries in the world. And now we do have a progressive municipality in place, leadership in place there in South Beach, and they are doing interesting things about this water quality and quantity problem as they're being flooded more often. But I also have the picture of an octopus there that was found in the storm drain of a parking garage, at which time everyone said, no, someone must have put it there. It didn't come up through the storm drain. And that causes my imagination to go, okay, we're gonna go out. Let's find an octopus and put it in a parking garage. That's a great idea. No, it came up through the storm drain because the sea is rising. And so this is happening. It's happening in a more sinister way than even what we see overland. It's happening underground, right, through this porous limestone, and it's zooming in to the interior of the system even faster as we extract more and more water out of the Everglades. And over the 15 years, in the past 15 years, we've lost 15% of our potable water supply in a population, in an area with a growing population. So when we forecast that out to the future, we really have a water supply issue going on in South Florida. And so we see stories like this in the Miami Herald, where the communities are pitting this dwindling drinking water supply against the struggles over worsening flooding, all of which has been very well addressed by this comprehensive Everglades restoration plan and plans that have built upon it in the 20 years since it was authorized into law. And so this is where the Everglades comes in, because it is such an incredible solution to a lot of what we're grappling with in this urban wildland ecosystem. And so I want to talk a little bit about our long-term ecological research program down there. We're studying the southern tip of the Everglades National Park here. Shark River Slough is one of the major drainages going out to the Gulf of Mexico, and Taylor Slough, a secondary drainage coming down through Florida Bay and into the Gulf of Mexico and the West Coast. And we study there the ways in which pressures like sea level rise happening more and more quickly, and tropical storms and other kinds of disturbances interact with the ways in which we move water around on the landscape through management and engineering and infrastructure changes, and how that plays out in terms of ecosystem structures, functions, and also the services that are provided back to the folks who are dependent on it. And we do that through necessarily making lots of connections across institutions that represent different kinds of scientists with different goals. So we have different universities collaborating, and we don't just work with agencies through these kinds of boundary organizations. We do have them, they do incredible work, we do work closely with them, but the way that we do that is through science co-production, where we have managers and agency scientists at the table at every single phase of the work that we do, every single phase. We talk to them every day. It's part of who we are as a program. And through that work, we understand this ecosystem better, and we understand how to manage it better for the services that it can provide. And we do that through long-term research at these sites distributed along those two flowways. We study everything from the hydrology to the plants and animals, and those sites represent all the different ecosystems, from the freshwater ridges and sloughs down through these incredibly productive mangrove forests, some of the most productive forests on the planet, with like 6-meter deep soils underneath them, and out through our estuaries, including Florida Bay, that's all overlain with this wonderful seagrass meadow. And this is just a little cross-section of those gradients to show you a little bit more about what they look like and what we've learned about them. So we've got Shark River drawn out here and the Taylor River down here. And the productivity gradients represented by the freshwater marsh into the mangrove forests as you go to the coast. And something that's very noticeable, well, really along most coastlines, is that the more productive areas are right along the coast. And typically that's because estuaries are pumping all kinds of materials to the sea. But in the Everglades, something very different is going on. The upstream ecosystems are hyper-oligotrophic. They hardly have any phosphorus, which is the limiting nutrient out here. And so instead, the Gulf of Mexico, which also doesn't have a lot of phosphorus, but has a little bit more than what's available upstream, is actually fertilizing those coastal forests as it moves in and out with the tides and occasional tropical storms. And it does it in a different way in this slough than this slough, because this one is more connected to that supply. And this one is a little bit more disconnected because it has Florida Bay in between. And in this one, the water actually moves underneath. And it comes up kind of over here and stimulates a little bit less productive mangrove forest. And so we call this the Everglades upside down estuary. And we're changing that as upside down estuary because we have such little fresh water now coming in and lots more marine water pressure as a result of sea level rise and the reduced freshwater head. And that marine water isn't just bringing salt, it's bringing the fertilizer fuel of this ecosystem, phosphorus. And so our long-term studies are showing all kinds of changes in both of those variables. We have a system of monitoring wells where we measure salinity. This is summarizing some of the work from Renee Price's lab, showing salinity contours moving to the interior of the ecosystem over just the short 10, 20 years that we've been running this program. And in the sites that border, or that are in between the freshwater and the mangrove brackish water ecosystems, we call that area the ecotone, we see this very rapid rise in salinity, and we're seeing that all throughout the system. Now we're also seeing, as that salt comes in, phosphorus as well. And John Kamenowski talked about this earlier today. We're seeing this trend of increasing phosphorus concentrations in those coastal wetlands, particularly in the Shark River Slough, but they're also moving to the interior of the system quite rapidly over the period of record, stimulated in some ways by storms that come through, but also occasional droughts, as well as this uptick in the rate of sea level rise. Salt, as it moves through limestone, also pops phosphorus off the limestone, and it brings more fuel into those forests. So what do the forests do? Mangroves are really very salt adapted, and when they get a little bit more salt, they're okay, and when they get a little bit more phosphorus, they're really happy, and so they begin to invade, particularly in these areas where there's less fresh water moving in. Mangrove transgression is the whole entire history of the Everglades. Over the last 5,000 years, this has been happening slowly. Over the last 50 or so years. It's happening really fast. Over a kilometer and a half of transgression has happened in some of these areas that have been cut off from their freshwater flows. Now these trees are more productive than the marshes upstream, the freshwater marshes upstream. And so they're laying down soil, and that building of elevation is really important in coastal wetlands whose future is really dependent on keeping up with that rate of sea level rise. So we're quite concerned about that, and we measure it using a distributed series of sediment elevation tables that gradually measure that rise, as well as we take a lot of sediment cores. And this is a transect, 3 transects of cores going from the marine to the freshwater end of the system. And the data here are the accretion rates measured in those cores averaged over 100 years in green and over 50 years in red, and the last 10 years in blue. And you can see that the rates of accretion, in fact, over the last many years, 100 years, is equivalent to the 100-year average sea level rate. But in the last 10 years, the sea level rise rate, 10 years before the core was taken, in 2013, was 6.9 millimeters per year. And what was happening in these forests averaged 3.4 millimeters per year. And so the forests aren't raising elevation fast enough. That means water is flowing in from the sea. And it means that it can get into the interior of these marshes that can't handle it, the freshwater marshes. And these marshes are full of sawgrass. That's our foundation species of plant. And that's a freshwater plant, and it sees salt, and it can't handle it. And what we're seeing in this area is, this is an area where the sawgrass marsh meets right up against the mangrove forest. Huge holes forming in the landscape, deep holes that are all filled with dissolved organic carbon that represent thousands of years of peat that has collapsed underneath previous sawgrass marsh. And we've been doing tons of experiments at all scales to figure out what's causing that. Is it the microbes going to town? Is it the plants dying and the roots falling away? And in fact, what we're learning is that it has a lot to do with the latter. The microbial communities can change quickly to more salt-tolerant communities, but the plants are dying. The root zone, when exposed to just a few parts per thousand above what they normally see, they die. And then the roots are no longer consolidated. They are easily mobilized to the surface waters, and we lose elevation, as shown here, on the order of centimeters per year. We're seeing losses like this, collapsing components of carbon throughout this ecosystem, including in the periphyton. I couldn't leave periphyton out of this talk. It's a big synoptic talk about our ecosystem, but the periphyton has been stimulated by this as well, and by salt and by phosphorus, both of which cause the very prolific mats of algae that are very diagnostic of this ecosystem and contribute over half the primary productivity of the freshwater marshes. Those mats are dissolving. We're losing the endemic cyanobacteria, the endemic diatoms, and converting, again, areas of marsh to open water as a result. The same thing is happening all the way downstream in our Florida Bay. Florida Bay gets hypersaline during times of drought, and when there's not enough fresh water being released into the Everglades, the seagrass die. They get, the hydrogen sulfide goes up. Often these are times of high temperature and there's less oxygen in the water, and the hydrogen sulfide goes up and the seagrass die. We've seen this over our long-term record in the past when we had this bad combination of not enough fresh water flowing through the Everglades and drought. And we saw it again in 2016, 15 and 16, just when the meadows were beginning to recover their prior levels of productivity. So this is a major stressor in this ecosystem, and once again, we're mobilizing ancient carbon stores into the water column. And we've been doing a lot of budget development of carbon budgets throughout the ecosystem, from everything from our ground-based measurements of productivity and sediment cores and measurements of the fluxes of dissolved and organic and inorganic carbon in the estuaries, and our net ecosystem exchange from a bunch of covariance towers. And we bring all of this together to understand that historically this has been a place of carbon burial throughout the system, and that we have a significant carbon stock at risk here. That when we had ecosystem economists as a part of our team to evaluate the worth of that carbon, they put a number between 2 and an upper limit of 4 billion. So this is an incredible carbon store in this wetland that's at risk. And we see incredible concentrations of carbon moving out during big storm events. So after Hurricane Irma blew through in last fall, we had a huge amount of rainfall and a lot of water flowing through the system. All the locks and gauges were open, allowing water to move into the Everglades. And we saw the highest DOC concentrations in our some 20 years of record, really high concentrations. And we had never seen that before, even in really big floods and after our last similarly rainy and severe Hurricane Wilma in 2005. So we're quite concerned that some of this carbon that's being exported is the collapsing carbon from upstream, and we have a rapid grant from NSF to study that. So what does the future look like for this ecosystem? I'm presenting you a lot of sort of scary stories here. And so if we just project the future with sea level rise rates as we're seeing and anticipating, we have a lot of models at work in the Everglades, a lot of modelers, and we have an incredible Everglades landscape process model that shows us what the peat soils might look like along with other ecosystem functionalities. And you can see here by 2060, we're gonna see an incredible expansion of these deep water areas that were once wetland. So we're converting different kinds of wetlands to open water bays. But if we bring more fresh water into this ecosystem as planned through Everglades restoration, we can prevent and slow down this process. We're not going to completely prevent it, but we can slow it down, buying us time for more adaptive solutions. And there are a lot of those, and we talk about them a lot. And here is the results of a similar model showing the effects of Everglades restoration and pushing that saltwater wedge back out. And you can see that without that restoration, we have the movement of those deeper water areas all the way up to the interior of our freshwater slough with a 2-foot sea level rise. So our managers are yearning for this kind of information to say, what kinds of strategies work, what doesn't, what should we do about this potentially really risky future for the Everglades? And so years ago, whoa, what happened? We, there it is. Put together we used Carpenter's inspiration. I don't know what's going on there, but you guys probably know this paper that was built upon the 2005 Millennium Assessment that said, hey, let's think about the future in a different way. Given that there are all these uncertainties, we can come up with some potential scenarios for the future. And come up with collaboratively with pathways to reach those potential futures. And so we did that. We put together funding from NSF through our LTER, a big slew of support from our Everglades National Park partners. The South Florida Water Management District was involved, and very heavily our Everglades Foundation, an NGO, working very hard on this in our community. And they said, hey, we can do a scenarios approach to planning. We can put all these partners together and envision a future for all these different aspects of our ecosystem and use it as a guide for planning more effective approaches to restoration. And we produced some incredible imagery from this. This is kind of a complicated one, but a lot of the images that I showed you throughout this presentation were built from that collaborative effort, one really nice product. And so we have these different options. One of them shown here, option D, turned out to be the best bang for the buck of 4-to-1 benefit to cost ratio. So a $13 billion investment gives you $60 million benefits. We know that ecosystem economic valuation is not the only thing that's going to matter here. But we did put together those numbers, and they are making a difference in the way that we communicate these materials to our policymakers. And so here's a strategy building upon our Everglades restoration plan that can work to restore these different aspects of the ecosystem. This took a lot of work, a lot of scientific effort to produce these numbers and to produce the rigor to support these options. And so we put together a special issue of Restoration Ecology recently summarizing that work that's available for folks to look at. And one of the pieces was this economic valuation And you can see here a really important infographic that we're now using in all kinds of venues to explain how the people of Florida are so incredibly dependent on what we do to the Everglades, because there's a disconnect there, a long-standing disconnect that has resulted in this quagmire. And so graphics like this have been helpful. Conversations with our policymakers have been really, really fruitful. And one of them was with the former president of the United States, who came down to visit us on Earth Day in 2015. And I got to meet him after having run over my trash can in my driveway because I got so excited and I didn't look in the rearview mirror. And he gave the most inspiring speech, and he said, I want Sasha and Malia's children to be able to see the Everglades the way I'm seeing it today. And he said these things about this being so incredibly urgent. And then he went home and he put some legislation in place and together with, and really kind of drove an agreement with the South Florida Water Management District to do something. I'm getting choked up about it. I didn't think I would, but it's so incredibly important and it's such an incredible first step to restoration. We had a 1 mile bridge in the upper part of the Everglades, enabling a little bit of a trickle of water to come back in that was finished in 2013. And he signed into fruition a second 2.5 mile stretch to enable more water to flow directly into the slough that we have our LTR sites strategically set up since 2000 to measure the effectiveness of this. And we're already seeing just in a year of emergency operations related to Hurricane Irma, a return of deeper water slough in that area. And a related piece of legislation to block some flowways along the eastern boundary to enable more water to be kept into the Taylor Slough that drains into that Florida Bay that gets hypersailing. And so this picture I took just a few months ago with the National Academy of Sciences team that comes down to evaluate the effectiveness of restoration and report back on that to Congress. They do that every 2 years, and it's incredibly important to have that external review going on. And they were glad to see that finally, after whining for many years, and for good reason, that something is happening. In addition, so in order to get water down here so that these projects are effective in the southern Everglades, we need all the pieces of that option D that I showed you, including a place to store more water instead of dumping it out to the sea. And so that's been the latest piece of legislation to move through our Congress. And I was able to go up with the Everglades Foundation a few months ago to a summit in DC where we talked directly with the senators about this. They put me on stage to talk about this science in between Senators Rooney and Senator Nelson after hearing over lunch from Marco Rubio, all of whom were speaking in support of this legislation to get more water into a northern reservoir so that we can bring it south. And that was really gratifying to see. This bill moving through is still residing in the Senate, but we sure hope that it can move forward. Another way that we're building this kind of science-based advocacy is by training our students how to do this better than ourselves and to make it a part of their culture. And we're very lucky to have Senator Bob Graham still in our community, and we meet with him and he teaches us how to do this. And he lines up, these are our LTR students and collaborators, and he lines each of us up with a legislator that we can work with and help make good decisions. And it's super hard, but we can go to their offices and talk with their staffers and work on these issues together. Finally, I just wanted to talk about the importance of engaging communities beyond those that I've talked about, the citizenry. We do that in all different kinds of ways, lots of citizen science projects, but also we have a seminar series that we've been running for a long time that engages the arts and through all different means, from music to the different kinds of fine arts to dance. And we have an artist in residence who's taken up a love of diatoms. It's so awesome. And he makes these diatom sculptures in the gardens of Miami. And he puts the different ones on there that my students tell him are going to be around when the sea level comes up to there. There's going to be diatoms growing on a diatom that looks like them, which might be a little weird for them. And so finally, I just want to wrap up with this model because it's one that we're using. I stole it from, or I'm a part of this Urban Resilience to Extreme Sustainability Research Network that's testing this model across a bunch of different cities exposed to the kinds of problems around water that I showed you today for the Everglades. And it's suggesting that we really need these eco-biophysical domains, that's a lot of what I talked about, and the social behavioral domain, which I talked about a little, but really importantly, this techno-infrastructural domain, which we're hearing a little bit more. We heard a few talks this week during our meetings about the importance of being able to work with engineers and influence the way that water moves around in our landscape. I tried to purposefully make that look like a water molecule with an extra hydrogen bond. I don't know, but in order to like show that, you know, surface tensions occurs at molecular levels, surface tension occurs at global levels, perhaps by building connections. We can do this in the Everglades. We can teach other places how to do this, like the Pontinal. We're starting to work with them, and they are facing these same kinds of issues where they're starting to do some of the things we did 60 years ago where we were getting rid of water. Not good, and we don't want that to happen. And we can work together for global scale solutions in this way. Marjorie Stoneman Douglas, the grandmother of the Everglades, would have told us to do this. She said the Everglades is a test. If we pass it, we may get to keep the planet. And I just end with this closing slide, and I realize I talked too long. And I could have just said this whole talk in a song from the FCE songbook. That has the whole thing kind of wrapped up. And if you want to, you can Google it, because I think we sang it at the LTER All Scientists meeting a few years ago. But it explains the whole thing in a short 3-minute song. So I'm going to end there, and I'm glad to take any questions that you might have.